Is okay? Okay. The last thing that I need to say or talk about in this chapter, and then we'll start reviewing. So I want to finish 3.10, linear approximations and differentials. And in the last section, I will just talk about two functions, and three functions and their derivatives, nothing else. Okay. Let's look at the following scenario. We have a function. This is function f of x, and I have a point, let's say P, of coordinates a, comma,
f of a.
Thank you. And now I would like to determine the equation of this line that is tangent at point P. So I have a point, and I would like to determine the slope, because I will be using y minus y1 equals the slope times x minus x1 to determine the equation of the tangent line to the graph of f of x at point P. Can anyone tell us? So obviously x1 is a, y1 is f of a. Can anyone give us the slope?
Instantaneous to, well,
Yeah, how much? What do you replace it with?
f prime of x.
Thank you, of a.
Oh, yeah.
Very good. That is it. The slope of the tangent line to the graph of f at P must be f prime of a. Right? So the slope of this line is f prime of a. We know that. The rate of change of the function with respect to a at this point must be the instantaneous velocity, must equal the slope of the tangent line at that point. Okay? So therefore, this equation becomes, can anyone dictate? And I'll write it.
Y minus f of a equals f prime a times x minus a.
Excellent. Allow me to move this here like we always do. We solve for y. Oops. Would you agree that this is the equation of this line tangent to the graph of f at P? Okay, I'm going to write it. Equation of the tangent line at P to the graph of f of x at P. Agreed? Okay. This has a very interesting explanation why we need this. And here it is. So this whole thing is called the linearization. The linearization of f of x. Very important what follows now. Near a. So near this value a, or around value x equals a if you want. So what does this mean? It means that at every point on the graph, I can find the equation of the tangent line, and I could use the equation of the tangent line to approximate the value of the function at this point. So here I will be using this tangent. Here I will be using this tangent. The key is near, because if you want me to evaluate at this point, you can say just approximate the function here. I don't care about the specific exact value. I cannot use the slope, I cannot use the equation of this, right? I have to use an equation, the equation of the tangent line at this point. And if I zoom in, imagine that I zoom in to this point, look how close the line is to the actual function. When I'm very, very close to this value a, it doesn't matter that much if I use the line to evaluate the function or the function itself. And this happens at every point. You can say, let's make our life easier because the fifth decimal, it's not important. So in that case, I will find the equation of this line and I will evaluate it instead of the function near a. So in other words, I can linearize any function at any point I want. So any function you can think of, you can find the equation of the tangent line at that point, assuming the function is differentiable there, obviously. So at any point, you can replace the function by a line, but not everywhere, just very in the vicinity of that point. So the function or the tangent will give you pretty similar results. Now let's look at an example. On page 255, let's find the linearization. Let's say problem 1 on page 255. And we are given a function f of x equals x to the fourth plus 3x squared. And we are given a to be -1. And I know that the linearization is uppercase L, L of x, which is f of a plus f prime of a times x minus a. When you get to Calc 2, you will see that this is Taylor series. But you have to wait till then. Okay, so I have a, which is -1. I have f of x. So in order to find the first piece, I only plug in -1. -1 to the fourth is 1. So f of -1 is 1 plus 3, which is 4. Do you agree with 4? So this is 4. Then I have to find f prime of x, which is 4x to the third plus 6x. Then I have to find f prime of -1, which is -4 minus 6, which is -10. So now can anyone dictate the function that replaces the original function? It's a linear function that replaces the original function near -1, very close to -1 on either side. So it's 4 minus 10, and in parentheses x plus 1. And this function will be -10x minus 10 plus 4 is -6. So what I'm telling you is this. If you want to evaluate the function f of x, if you want to find f of -1.001, or you want to find f of -0.0009, don't bother with the function. Use the line. So plug it in here, and you will see it's extremely close to that. And this is the time I would like to take a second and show you with a graphing calculator. So here it is. So I will put these two in y equals. y1 and y2 will be those two functions. In y1, clear if you have anything else in there. So in y1 I have x to the fourth, and then I have plus 3x squared. Of course, I always do that with the software. X to the fourth outside plus 3x squared. And then the second function is the line, which is -10x, and then -6. So now go to second and table. And let's punch in -1. Let's punch in -0.009. Oh,
0.99.
of course, that's what I meant. Go up. Okay, that's what I meant. That's why I was looking at. Something is wrong. Okay, minus 99999. And then minus 1.0001. But if you deviate from that and say, oh, let me use this, that would be silly. But let me be silly for a second. And let's say, oh, let's use this function, the linear function at -2. You can't do that, because the linear function approximates the original function only near -1. If you want something around -2, then you have to create another line, another linearization specific for that point. Which would you prefer, assuming you did not have a calculator? In which of these two functions would you plug in -0.998? In this and raise it to the 4th and then square, or in this, knowing that the difference is almost inexistent, non-existent, right? Ready to continue? Okay, so this is what is called the linearization. Any function that is differentiable at a point can be linearized, can be replaced by a function, by a linear function at that particular point, around that particular point, very near that point. Okay. Now, if you remember, we looked at the following scenario, and this is, I would say, very important. So please bear with me. Here is our function, f of x. This is a point. Point P with x f of x, of course. And this is point Q. This sounds like what we talked about 2 months ago. And this is point Q, very close to P. What will be its x coordinate if it's very close to P? A little bit. Very good. Delta x. And what will this be? So now, no, not yet. So now, this is the idea. I have a function, I have a point of these coordinates, x comma f of x, and I would like to know, so here's a real life situation. Let's suppose we manufacture discs of metal. And I know that I cannot always be exact with a diameter of 1 inch. I know that. The machine has a tolerance. If I do it on my own, I cannot create all discs with a diameter of 1 inch. And I want to ask myself this question. If there is a minor error in plus or minus in the diameter of the disc, let's say of 0.1 of an inch, I make an error in the diameter of the disc. How will that affect the area of the disc? What will be the error that will occur in the area of the disc? I know that my error will be 0.1, right? How much will that create of an error in the area? So the area is the function. This is x. That's the diameter. And I want to determine the error in the area. So now, so assuming that this is, in my example, the area of the disk, for a delta x change, let's say in the diameter, what will be the change in the function? The exact change that will occur in the function, how do I find it? So in other words, I don't have x, I create a disk with x plus a little bit. So what will be the change in the area? This is the area for x, and this is the area for what I'm creating. So what will be the exact change for a change in x? The exact change in y for a delta x change in x. We will call it delta y. Exact change in f of x for a delta x change in x. So can anyone dictate now what is delta y?
X plus delta x minus
Excellent. Is it clear? It's this distance, right? This is delta y. Would you agree? Perfect. Like before with the linearization, I want to find an easier way. I don't want to punch in 1.001 in the function. I don't. I want to find an easier way, which may give error, but it's an easier way and I'm happy with it. Okay? Of course, I am going to draw a tangent line at P. I am going to extend this line, and I'm going to extend this line. And obviously now I have a right triangle. Now, can anyone tell us what is this distance? Of course, it's the same thing, right? Now, can anyone tell us what is this distance? It cannot be delta y. Delta y is already taken. Delta y is the exact change in y, or in the area in my example, for a minor change in the diameter of the disk. Yes, please, Chris?
It's f prime of x times delta x.
Well, it's, first of all, is denoted by dy. And this is also the same thing with dx. Delta x and dx mean the same thing. They are measured the same way. They have the same length. So now I know that the slope of this line is, for this point, what? Indeed, f prime of x, right? But the slope of this line is also rise over run. So I have two ways of expressing the slope of this line. So f prime of x, slope of the tangent at P, or m equals f prime of x, which equals rise over run. I know another notation of f prime, and we used it over and over in implicit differentiation. What is that notation? dy over dx. So therefore, this quantity must be dy, because this is dx. So f prime of x must equal dy over dx as we knew it. But we didn't know, when we were using the notation, we didn't know that this has a significance and this has a significance. We only thought, because we didn't talk about it, we only thought that f prime of x, oh, okay, I can replace it by dy over dx. It turns out now that dy has a meaning. It's not called the exact change because the exact change is not this. This is the exact change, right? Also remember, Q and P are very close to each other. I will never have this much of delta y and this much of dy. They are very close to each other, but I have to zoom in order to explain what I'm doing. So dy is called the differential of function f of x. Dx, it's the change in x, but it's also called the differential of x. And here's my claim. What do you think the relationship between these two is? You tell me and I'll put it in.
The delta of x.
No, delta y. This is the differential, the exact change in y and the differential of y.
Okay, so it represents sort of.
What is the relationship between these two?
They both represent rate. Well,
The relationship.
they both can be used for rates.
In other words, what are you saying? You're on the right track. I'm looking for a word or a symbol or something to write between these two. Okay, I'm going to put some symbols on the side and you'll tell me which one you think.
Okay, greater than or
Exactly. Exactly, that's the key. They, like with a linear approximation, because evaluating the function near a point or evaluating the line is very, very close, and they are very, very close even on this, right? Then these two are expected to be very close to each other, right? That's what I was saying, that Q is very close to P, and there is no such big difference between this and this. But if you say, oh, delta x is 5, then this will be tiny and this will be big, or who knows, but the other way around. But if you're talking about tiny difference in x, then these two should be right on the money. And yes, you will not want to do this. You will want to determine this. Now, I would like you to tell me what to write on the left and what to write on the right. There is one more step to this relationship. What do I write for the left? What does it equal to? Yes. F of x plus dx. I'm going to write dx because they are the same. And then, yes, approximately. And from here, I would like you, from this relationship, I would like you to solve for dy. How much is dy? Cross multiply and solve for dy. So it's f prime over 1 equals dy over dx. So what should dy equal to?
F times x dx.
Very good. One last step. I'm moving f of x. So f of x plus dx is approximately f of x plus f prime of x dx. Does this resemble anything? F of x plus f prime of x, where a is x, and a little bit of x, which is the distance between x and a. It's really the same thing. How do we use this and what does it mean? So let me put it in words now. This piece is f of x plus a little bit, which is approximately f of x plus a little bit of y. Don't show this to anybody because it's mathematically is not improper, but it doesn't really have math in it. It's a way of remembering what this means. So if there is a little bit of change in x, that is the same with the original f of x for that point, plus a little change in y. Okay, so now here is the question. Fine, beautiful. When am I going to use this, right? And here is my explanation, or one example. So let's say I want to determine the square root of 99. Can anyone give us three different things here? The function we are talking about, the point or the x value we are talking about, and the change in x that we are talking about. What function? Obviously, the square root of x. Obviously, x is something simple that I can determine the square root from, which is?
Something simple, 100.
Of course. What is the little change away from x? Minus or positive? Right. So using all this, please tell me what to write. I need to find the square root of 100 minus 1, which is the square root of 99. So the square root of 99 is this, which is the square root of 99 minus 1, which is approximately, because I refuse to take the square root from 99, it will be approximately what? Very good. Now I need to find f prime, but I know f prime for the square root of x. I learned that a month ago. I will never remember. I will never forget that. I don't have to. Okay. So then it's plus multiplied by -1. So now I'm going to ask you in a moment, after we finish this, which is 10, and this is -1 over 20, which is 200 minus 1, which is 199 over 20. So which one would you prefer to calculate, the square root of 99 or 199 over 20? And here it is. The square root of 99 or 199 divided by 20. Everyone can divide 199 by 20. There is no discussion there. Which of these two would you live with? Right, the top one is the exact difference. No questions asked. But this is the way they determined tangent 44 degrees. No one can find tangent 44 degrees. You may be able to find the square root of 99 by hand. But I don't know how many years ago, nobody knew what tangent 44 degrees is. They had to invent calculus to determine tangent 44 degrees. Okay, so then what am I asked to find? This is the same with tangent of what? Oh, of course, I'm sorry. Sorry. Nobody knows how to find tangent 44. Is approximately, for sure, equal to what?
Tangent of 45 plus secant squared of 45.
Since in calculus, I cannot use degrees, I have to change 1 degree, because it's -1, into radians, multiplied by pi over 180. So now let's put it in and see what we get. Well, of course, I know on the right-hand side, I have a 1, because tangent 45 is 1. I have a negative pi over 180. And secant 45, if you remember, secant 45 is 1 over cosine squared, right? Secant squared 45 is 1 over cosine squared 45. And cosine, so this is 1 over the square root of 2 over 2, but squared. So this is 2 over 4, so this will be 2, right? So times 2. So now let's look. Make sure your calculator is in radian mode. Yes, it is. And now let's calculate tangent 44. And then let's calculate our 1 minus 2 times pi and divide that by 180. What did I mess up? I put 2. I messed up something.
You have to put the 2 pi divided by 180.6.
It's separate.
Oh, it doesn't matter. It's still, the calculator will do 2 times pi and then divide everything by, yeah.
Oh, so it's not.
So let me see what I messed up. So 45 minus 1, that's correct. And then 45. And then tangent squared, yes, tangent prime is secant squared. And then multiply by negative 1. So, right, 180 is pi radians. So 1 degree will be pi over 180. And one more time, secant squared is 1 over cosine. Cosine 45 is the square root of 2 over 2, which will be 2 over 4. When I square that, I get 2. So it's 2 pi divided by 180. Tangent 45 plus secant squared. You think this calculator,
Isn't tangent of 44 degrees?
so 1 minus 2 multiplied by pi and divided by 180. Yeah. And tangent 44. Obviously, I messed up something, but I don't see what. They have to be very close. So tangent 44 is 45 minus 1. Tangent 45 is 1. F prime, tangent prime is secant squared
Well,
of
it's supposed to be
45.
1, right? Your tangent 44 that you put in was not in degrees.
Ah, thank you
See,
very much.
that's what I.
Thank you very
There we
much.
go.
Thank you, thank you, thank you. Thank you, thank you, thank you. Excellent. Of course. So tangent 44, very good. It has to be that close. So this was 0.96568877, and our calculation was 0.96500934. So they had to wait to invent calculus to determine tangent 44. So there is nothing wrong, but thank you so much, Eric. I put tangent 44 instead of having it in radian, in degrees. I had it in radian. Thank you. Any questions? And I'd like to work on some problems in a minute. But the last, yes. Any questions? You want to start? Maybe you want to start with that. Let's look at first of all finding some differentials, and then looking at a couple of problems. Thank you for telling me that. Okay, so find the differential of each function. So let's say problem, you choose 11 through 14. 12 it is. 12 on page 255. And this is y equals, you want a or b? Let's do one of them. One is s over 1 plus 2s, and the other one is e to negative u cosine u. B. Okay, perfect. So this is e to negative u times cosine u. We're asked to find the differential of this function. By definition, this is dy, which is f prime of x dx. In this case, I have u, not x, so then it will be dy equals f prime of u times du. So dy, I will differentiate the function. It's a product. The first function prime is e to negative u times the inner function prime times cosine u. And then plus e to u cosine u prime is negative sine u times du. I will rearrange it a little bit, and I will rewrite dy equals negative e to negative u cosine u, and then minus e to u, I'm sorry, this was negative u, multiplied by sine u du. And this is the differential of function y. Just f prime dx or f prime du. Any questions? Find the differential dy. Evaluate dy for the given values of x and dx. 15 through 18.
17.
Good. So we have 17. Y equals the square root of 3 plus x squared. X equals 1 and dx equals negative 0.1. They want us to find the differential of y. Let's find the differential of y. What do I have to write? The definition is f prime of x dx. This is the differential of y. When I differentiate y, or y prime, I get 1 over 2 the square root of 3 plus x squared multiplied by 2x, and I simplify. So then y prime equals x over the square root of 3 plus x squared. So therefore dy is, can anyone dictate?
It's x over
Yes.
3 plus x squared dx.
That's it. This is a differential of y. Now they're asking us to replace x by 1 and dx by negative 0.1. So dy equals 1 over the square root of 4, which is 2, multiplied by negative 0.1. So then dy will be 0.5 times negative 0.1, negative 0.05. Now they want us to compute delta y and dy. 19 through 22. So they want us to compute delta y, dy for, let's say 21. So we want to compute delta y and dy for 21, which is y equals 2 over x, or 2 times x to negative 1. They are giving us x equals 4 and delta x equals 1. So delta y by definition is f of x plus dx, this is the same with dx, minus f of x for the given x value. So in our case, this will be f of what? Plus 1. So f of 5 minus f of 4. So f of 5 is 2 over 5 minus f of 4, which is 2 over 4. The least common denominator is 20, and 4 and 5. 4 minus 10, negative 2. So this is negative 1 over 10. So for a change of 1 unit in x, the y value or values change by negative 1 over 10. So for an error of 1 in x, the error in the function would be negative 1 over 10. The exact. But now I want to determine the same error but using dy, which will be, when I differentiate this, I have negative 2x to negative 2 times dx. By definition, dy is f prime of x dx. And this is f of f prime. So dy, one more time, is f prime of x dx. So all I have to do now is calculate. Negative 2, x is 4. So 4 raised to negative 2 times x, which is 1. So this is negative 2 over 16, which is negative 1 over 8. So let's look at, I know we don't need a calculator for this, but let's see it. Negative 1 divided by 10, which we know what it is. I should have not even put that in. And negative 1 divided by 8. There is a difference because delta x is huge. 1 is huge. So that's why we see this difference of 0.025. But if for the same function I'm looking at 0.01, then the difference will be much smaller between the two. Okay, I would like to look at 25.
So,
Yes, please.
In my further on, in the distinction between the delta of x and the d of x, would it be okay?
Delta x and dx are the same. You're talking about delta y and dy?
Yes, ma'am. But I usually use the delta x for just differences that aren't necessarily infinitesimal, and then the d of x that's just sort of the.
That is true. You can say that, but when we talk about differentials, for now, delta x and dx are the same. And even later on in the limit of the Riemann sum, they will still be the same when we get to chapter 5. Still, delta x and dx are the same value. Yeah. In 25, we have the cube root of 1001. And this is the same with the cube root of... Yes, please, Sarah?
Yes, switch back to screen.
Oh, yeah. Sorry.
You're fine. You gotta switch it back, yeah. There you go.
When I put back the page instead of... Okay, so the cube root of 1001 is the same with the cube root of...
1000
Yes,
plus
plus 1. So this is approximately the same with... Of course, you have to give me 3 things. You have to give me f of x, you have to give me x, and you have to give me dx. And then, of course, you have to find f prime. What is the function?
Cube.
Very good. What is x?
1000.
What is dx? And so this is x to 1/3. So 1/3 x to 1/3 minus 1, which is negative 2/3. Or I could write it as 1/3 the cube root of x squared. If that's easier, I don't know. We'll see in a moment. So what does this equal to? Remember, f of x plus a little bit is approximately f of x plus a little bit of y. And the little bit of y is the differential of y.
So it's the cube root of 1000. Should be 10, right?
Not yet. I just want everyone to see what it is, but yes, you're right. So plus 1/3 the cube root of 1000 squared multiplied by dx, which is 1. So f of x plus f prime of x dx. So now I can calculate, you're right, this is 10. The cube root of 1000 is 10, but I have two of those, 10 times 10. So this is plus 1 over 300. So this is multiplied by 300. So 3000 plus 1, 3001 over 300. So we take the cube root. What I'd like to do, I don't like the cube root, so I just put 1001 in parentheses, caret in parentheses, 1 divided by 3. And press enter. And then our function, 3001, the line, divided by 300. It better be extremely good. Extremely good. So now this is what I think, you know, it will make more sense. Like, for example, problem 34. Do I still have time? Okay, last problem, I promise.
7 minutes? Yeah, 7 minutes.
I have 7 minutes?
I don't know time class.
It's 8:13.
8:25.
Yes, so I have 10 minutes.
Yeah, please.
Okay, very good. So let's read the problem. The radius of a circular disc is given as 24 centimeters with a maximum error in measurement of 0.2. I refuse to read on before I identify what this means. So it says the radius of a circular disc is given to be 24 centimeters, and I'm told error in measurement of 0.2. What does that mean?
dx is 0.2.
In this case, dr 0.2. Excellent. Now, part A. Use differentials to estimate the maximum error in the calculated area of the disk. So can anyone give us the area of the disk? And after that, please tell me what we are asked. Use differentials to estimate the maximum error in the calculated area of the disk. I'm not asked, it should say estimate. It says estimate. Oh, okay, I'm sorry, it does. I'm not asked to find the exact error in the area for a 0.2 error in the radius. I'm asked to use differentials to estimate the error in the area for an error in the radius of 0.2.
You're pretty much going to use the same formula as before. So you would
But what am I asked to find?
you're asked to find the area of the
I'm asked to find the differential of A. Yes, I'm asked to find dA. This is the question. So let's start with the area. Remember, we have dy equals f prime of x dx. So I'm asked to find dA as a prime of r dr. This is the question. This would be the error, the estimated error. So an area for the disk. Pi r squared. Now let's find, for this function, let's find its differential. So dA equals 2 pi r times dr. So now I will evaluate it for r equals 24 centimeters and dr equals 0.2 centimeters. So this is 2 pi 24 times 0.2. I will put everything in the calculator and come up with an error. 2 times pi times 24 times 0.2. 30.1593. What? Careful.
Square centimeter.
Very good. So for an error of 0.2 centimeters in the radius of the disk, what is the estimated error in the area of the disk? 30.1593. What is the relative error and what is the percentage error? Okay. So B, relative error is error over original. So the error is 2, no numbers just yet, 2 pi r dr. What is the original? Pi r squared. Look at this. So this is twice dr over r. So it's twice as much as the error, as the relative error. Twice the relative in the radius. And now they want what is the percentage error. How do we determine the percentage error?
Calculate what the area of the original should be
And
see, and then divide the 30.1593
by the original.
by the original.
Very good. So the percentage error is the area divided by original, error in the area by the original area. So what was it? Pi r squared, so this is pi multiplied by 24 squared times, oh no, we already calculated that. So 30.1593, I don't need that. Divided by pi multiplied by 24 squared and multiplied by this, that's it, right? Pi r squared, good. So if you have the number, give it to me. And it has to be in percent. We already determined that. So this divided by pi and further divided by 24 squared. I got 1.67%. I know I have only 5 minutes, but I need a little bit more than 5 minutes to explain to you what the hyperbolic sine, hyperbolic sine, hyperbolic cosine, and hyperbolic tangent mean. And this is the last section, 311. So these are 3 new functions that I would like to mention, show you how they look like, graph them, and only find their derivatives. And I'll give you an example. One function, which is hyperbolic cosine. If you, when you drive, even in little towns, you will see telephone poles. So this is one telephone pole and this is another telephone pole. And the way they calculate the length of this cable between this point and this point is using a hyperbolic cosine function. That's one of the very common applications of hyperbolic cosine. But I have to tell you what hyperbolic cosine is.
So you're talking about the length between
Yes.
the two
Yes.
Oh.
Yes. It follows a hyperbolic cosine function. Yeah. And I did shut my book, but I shouldn't have, and I can show you. I can't think right now of other applications. This is the one that comes to my mind right away. So this is it. It uses a hyperbolic cosine function. 20 hyperbolic cosine of x over 20 minus 15. So this is the shape. But I'll explain what they are and how they came up with them, and the graphs are. Oh yeah, and also the ocean waves follow a hyperbolic cosine function. And this is hyperbolic cosine, hyperbolic tangent. I know it's very similar to something we know very well. And this is hyperbolic sine, hyperbolic sine, hyperbolic cosine. And look at this. It's like arc tangent x. Yep. But it's not between negative pi over 2 and pi over 2, but between negative 1 and 1. And this completes chapter 3. And then when we move on to chapter 4, there are more applications. And in chapter 5, we'll look at integrals.